going to go ahead and introduce the first speaker, Dr. Tim Riles. Tim is a professor and director of the UT Center for Renewable Carbon. He joined the university following 13 years with the U.S. Forest Service Southern Research Station in Pineville, Louisiana, after 2 years on the faculty of the University of California at Berkeley. Tim's research career has focused on the efficient and effective utilization of renewable resources in advanced composite materials, including the development of high-throughput analytical methods for characterizing wood. As director of the CRC, he facilitates UTIA's research and development program on the use of forest and agriculture biomass for alternative liquid fuels, industrial chemicals, and advanced materials. And I will give it to him. Thanks so much.
Thanks, Jessica, and welcome to everybody. It's great to be here on this National Bioenergy Day, and I appreciate the opportunity to talk to you a little bit about feedstock-related issues as we think about advancing the bioeconomy and building the bioeconomy, including fuels and chemicals, other materials as well. What I'd like to do this afternoon is to highlight what I consider at least some recent progress as a part of some of the larger programs that have been ongoing in really across multiple institutions and organizations in recent years, and where we stand and where things are headed as we move the challenging question of feedstock down the pike. So. Why the focus on feedstock? I guess from my own perspective, we really see that as the foundation of the bioeconomy. After all, we're very much challenged with providing a reliable and a consistent and a sustainable source of biomass to an emerging industry, whether it's chemical production or fuel production or other products. So at the very outset, or the very foundation of this new industry, feedstock and biomass production is a real key. I'll tend to focus my comments and emphasize the southeast region where I'm most comfortable, but I think a lot of this information really reaches across the nation. One of the aspects of biomass production that I've become aware of over the course of the last several years and being involved in this is we have a number of advocates for different types of biomass sources and biomass production systems, and it's fortunate that we do, because really the need as we move forward and think about the demand from our land, it's important that we begin to think about developing a broader portfolio of biomass resources to again address that challenge or that issue of a sustainable supply and a reliable and consistent supply of feedstock to an industry. You know, when we look at the southeast, we're fortunate to really benefit from the capacity to build or to produce a lot of different types of biomass sources, and that really is contributing to a broad portfolio for this region that we think ultimately will be a real benefit. When we think about really where we are today and where things are headed, it's I think instructive or useful to back up just a little bit. The southeast, of course, has a very vibrant and very active forest products industry that really is built on a broad base of southern pine and other hardwood materials across the region. When we look at southern pine or think about southern pine, and especially how it relates to the current industry, it's through the activities and the operations that are providing feedstock or raw material to pulp and paper and the forest products industry. And in fact, we're generating quite a bit of residue. And the important point here is that residue really is a resource, a biomass source that is available to us today. It's on the ground. And in many ways, I see it as an analogy to the corn stover of the Midwest. So clearly an obvious starting point and a reasonable starting point for this particular region. But I think in many ways the real interest and the real appeal comes as we start to target and address and develop dedicated energy supply or energy crops, things like short rotation woody crops, things like perennial grasses and sorghum and other sorts of supplies for the industry. This portfolio really addresses a number of potential benefits and things that we need to be aware of in moving ahead. Number one, it allows us to really address the interests of a diverse collection of landowners in the southeast and in the east in general, where most of the land is privately held, and there are very diverse interests and goals from individuals across the region. It's valuable to have these production systems available, or these production system options available for them to consider. You know, as we really highlight issues of sustainability and productivity, yield is certainly a key characteristic or a key consideration as we move forward. And this portfolio or this suite of individual crops allows us to consider approaches to maximizing the yield as we begin broader energy crop and feedstock production. Numerous other risks as well related to maximizing or optimizing ecosystem benefits, reducing risk from disrupted supplies, just to be able to ensure production of and supply of biomass or feedstock to an industry in a 24/7, 365 kind of framework. This diversity really comes to play. The important topic, or important point maybe as we move along and we think about integrated feedstock supply systems like this, is that we see an increasingly robust industry as well that is able to accommodate different feedstocks and different biomass sources as they become available. One of the programs that, in my opinion, has made a real impact over the course of the last 6 or 7 years has been one that was developed by the Sun Grant Initiative in partnership with the Department of Energy, Bioenergy Technologies Office. It's called the Regional Feedstock Partnership. This program made a number of important contributions and really I think in many ways elevated the issue and the opportunities of feedstock production and energy crop production in particular to an appropriate level. The program really engaged a number of researchers across the nation, gathering the experts in different production systems and different crop systems that was absolutely necessary and really led to some very valuable products and outcomes from the work. Focus areas included corn residue, and there were some very, I think, practical and impactful outputs from the corn residue work, addressing issues of stover removal rates and sustainability that were very important and very valuable in a number of subsequent analyses. Similarly, with the residue front, or on the residue front, looking at wheat and cereal straw residues, availability, and the prospect of those materials as well. The other piece that was considered within the Regional Feedstock Partnership was also forest residue. This was largely a paper study. I feel like in many ways production of pine and forest resources is something that we have an industry and familiarity in terms of logistics or production logistics around that. So not a great deal of emphasis in the RFP on forest residues. But instead, again, the energy crops representing a very real opportunity for this industry moving forward in providing the kinds of feedstocks that are necessary for growth and for efficiencies. Considerable work was invested into the herbaceous and woody crop energy systems. A number of important products out of this I mentioned includes a couple of special issues in bioenergy research that consolidated the information and I think very relevant and valuable information. We've seen the work, the data moving on to other uses within the Department of Energy and USDA as well. The piece of the Regional Feedstock Partnership that I'm most familiar with and was fortunate enough to work most closely with was looking at short rotation woody crops and the advancement of short rotation woody crops. So maybe just a minute to discuss the short rotation woody crops technology. And in many ways, it's a very interesting production system. It's something of a hybrid in the sense that it involves trees in production of woody biomass, but it brings in more of an agricultural approach, so a much more intensive management approach to really maximize production and reduce typical rotation times for woody materials. So this would include, and as we look at the management approach, fertilization and weed control and other intensive processes like that to ensure maximum growth and yield from these materials. The program within the Regional Feedstock Partnership, again between the Sun Grant Initiative and Department of Energy, really focused on two different species that included willow, primarily in the northeast U.S., but also hybrid poplar. And hybrid poplar is of particular interest to us in that it really is a species that covers the nation and in fact the globe. So information can be really extended from one region to the other, and it has been an approach that has significantly advanced the value of this particular crop technologies. The program was really, the value, I think, of the program was really increased in large part because of the coordination as a number of trial networks were established across the nation. So coordinated in the sense that the same clone material, the same genetic material was placed in field trials or clone trials across the nation, allowing us really to assess the state of the genetic art, if you will, the material that's currently available to us, and really kind of baseline growth and yield potential for this particular source of energy, source of biomass. So a very unique and very valuable program that generated a tremendous amount of information, not only on growth and yield, but also on questions around production economics and system sustainability. Also generated a lot of new data, once again, in terms of yield and production potential that has been incorporated in a number of recent studies and ongoing studies to ensure that we have the latest and greatest information on this particular woody crop. Also, the opportunity to, because within the program we were generating lots of biomass, lots of that biomass ended up at the Idaho National Lab Biomass Library, providing further information on the chemistry and the quality of the material. So thinking a little more regionally at this point, the Ibis Partnership, this is a USDA NIFA-sponsored CAP project, one of several that have been installed across the country. The Ibis Partnership being focused in the southeast. The intent of the Ibis Partnership is really to address barriers to broader deployment of fuels and chemicals industry in the southeast. A primary barrier has to do simply with feedstock availability, and again, that supply and that sustainable supply of feedstock to a technology provider or to a converter in the region. We have, within the Ibis Partnership, addressed a number of energy crop opportunities as well as the southern pine residue opportunities for biomass supply, but have been particularly interested in advancing the short rotation woody crops. Now, when we look into the southeast, I should mention that as we talk about short rotation woody crops, and there is something of an emphasis on hybrid poplar and eucalyptus, it is a technology that lends itself to many species in the region. Sycamore, as an example, sweet gum, other types of hardwoods are ideally suited for the short rotation woody crops approach. Our focus in the southeast has been primarily towards hybrid poplar and eucalyptus, or at least within the Ibis Partnership. These have been the primary feedstocks that we have addressed. One of the goals within this effort, and I should mention, you can to give you some indication of the interest in eucalyptus, to have a look at the picture there. It's with Dr. B.J. Tamang from Arbigen, standing in a 2-year-old eucalyptus stand. Eucalyptus is just hard to ignore because of its tremendous productivity and the high-quality biomass that it produces. So we're very excited about the potential for eucalyptus, especially in the deep south, or as we tend to call it, south of I-10, where frost becomes less of a risk factor there. Excuse me. Also, within the Ibis Partnership, though, we've also emphasized hybrid poplar in our work within Ibis, and the hybrid poplar into things. We've really targeted on working to coordinate that with the regional feedstock partnership approach and data and trials that were in place to further that information and growth and yield. And to really look at importing this technology into the southeast. It's a little bit surprising that with all our experience in forest materials and woody materials with the southern pine plantations, that short rotation woody crop technology with the hardwood systems has not made or not had a real footprint in the region. We can look to the north central and especially the Pacific Northwest to better appreciate the advantages that it offers, and we're very interested in importing the technology and the systems that they have developed into the southeast to fully take advantage of that. So hybrid poplar has been extremely important to us, and the program has dealt considerably with kind of the process feedstock interaction question marks that remain out there. I should mention that Ibis is a partnership that's comprised of the University of Tennessee, North Carolina State University, researchers at Auburn University, as well as University of Georgia and Arbigen. It's been a really, I think, very valuable approach to addressing some of the more practical and pragmatic challenges associated with the deployment of this industry. Within the Ibis Partnership, a key or critical consideration as well has been sustainability, and it's something that we'll continue to keep at the front of our mind as we think about feedstock development for the industry. Maybe a little bit of detail and a little more information on the Ibis hybrid poplar program in the region. Feel fortunate in that really we have a number of different trials that are scattered across the southeast. When you think about production or yielding a new commercial variety, there are a number of steps involved. It begins obviously within the greenhouse, but then followed up quickly to clone trials, or clonal trials, where maybe a couple of hundred different clones are evaluated in the field for their performance. Selections are made. Yield trials become the next step, which are typically a little bit larger in scale and give us a better picture of growth and yield for any particular clone. and then on to demonstration. And we're excited to have essentially every leg of this process represented within Ibis, and continuing to advance the potential for woody crops and hybrid poplar in particular in the region. We've really emphasized yield trials. You know, one of the interesting things about tree genetics or poplar genetics in particular, that in many ways genetics are local, so it's very important that we identify which clones or which varieties are best performing in certain regions, and that's a big piece of what Ibis has been involved in with trials in North Carolina, Tennessee, Alabama as well, and most recently in Mississippi. The photo, the bottom right photo here, is of a new commercial demonstration that we put in place in collaboration with the Advanced Hardwood Biofuels Project in the Pacific Northwest, a sister project to Ibis that's funded by the NEFA CAP program. And also the partner in this is Greenwood Resources, and considerable contribution from Arbigen and other tree genetics experts in the mix. But as we look at things as a whole, you know, one of the things that we've seen and just kind of continue to confirm is that there really are a wide range in growth and yield characteristics between the different trials. So this is providing very valuable and needed information in continuing to down select for optimal clones, or the best clones for this particular region and for different sites. That's just highlighted in the bar chart there on the top right, that the heights really, this gives you some indication of the range of tree heights that we've observed for the different trials. So yield is absolutely important. It's central to sustainability questions and being able to provide and really optimize and maximize the production of biomass on the land across the region. So yield has been and continues to be front and center as we think about feedstock development and biomass supply options. But there's another piece to the puzzle, and that it has to do with quality. Yeah. So in the case of quality, it really is contingent on the output or on the particular technology that we're focused on. But just to highlight, in this case, for biochemical conversion, we're thinking primarily for biochemical in the short rotation hybrid poplar as well, we're plotting lignin content against cellulose content. And in the case of biomass, cellulose is for biochemicals, cellulose content is a particular quality metric, in that this has the sugars that the industry is particularly interested in. We've been surprised that there's a very wide range, observing a very wide range frankly, of both lignin composition and cellulose content. So understanding the chemical composition and the impacts that it has offers another very real opportunity to maximize efficiency and improve processes. So as we think about biomass conversion and the question of quality, it certainly has to do with the pieces that we're involved in or that we're particularly interested in, like sugars. But the other challenge has to do with the parts of the biomass that we aren't particularly interested in, that aren't actively involved or contributing to the products of a given process. Extractives, inorganics being a couple of obvious examples for us. And we've done some work, again, looking at hybrid poplar and the impacts that we have, or the variation in quality of this particular feedstock. Ash has been a real concern in thermochem, and it's something, thermochemical conversion is something that we're paying more attention to as time goes on. And this just to highlight that one of the question marks as we think about actual production biomass, for woody systems is that bark has a much higher ash content than wood, and consequently it's a consideration that has to be met, especially when we think about production of short rotation woody crops, where the bark content can actually be 10 to 15%, upwards to 25% of the biomass delivered. So it's a consideration that needs to be taken into account. We've recently started a new project with the Department of Energy VITO, Bioenergy Technologies Office, that is introducing considerations of feedstock quality. In particular, it's really looking at integration of different feedstock sources to maintain a consistent, reliable, and predictable supply of feedstock in the long run. We're excited about where this project is headed. So with that, I think in the interest of time, we'll leave. I'll let you read through the closing remarks, and if there are any questions or time for questions, I'll be happy to address them. There's no time. I talked too long. I'm sorry. But hopefully along the way. Thank you, everyone.
So our next speaker is Dr. Stephen Schmeling. Steve is a research assistant professor at the UT Center for Renewable Carbon. He received his PhD in inorganic chemistry from Vanderbilt University in 2010. Then he spent 2 years at the National Renewable Energy Laboratory as a postdoctoral scholar studying the catalytic valorization of lignin. Dr. Schmeling works with an interdisciplinary team of researchers at the CRC to develop novel integrated thermochemical conversion processes to produce fuels and products from lignocellulosic biomass. Steve is also interested in outreach efforts and workforce development to support the growing bioeconomy in Tennessee and the southeastern United States. So let's welcome Steve, and I'll hand it over to him.
Well, thank you very much for that introduction. Today I'm going to talk to you a little bit about some thermochemical conversion of biomass to fuels and other products. And I kind of want to give an overview of these processes that we use both in the course of the Ibis research that we do and just in general. We'll kind of talk about the engineering and science aspects of these processes. So when we talk about thermochemical conversion, there's essentially two ways to convert lignocellulosic biomass into fuels and products and other useful things. And those two are gasification and pyrolysis. So we'll talk a little bit about those differences now. Gasification is actually a series of chemical reactions that occur above 700 degrees C, where we heat biomass up to that temperature. And those reactions include things like dehydration, which of course is the removal of water, pyrolysis, which we'll talk about in a moment. Combustion, of course, is the reaction of organic materials with oxygen to produce CO2 and water. And also gasification, which is the reaction of carbon with water to produce carbon monoxide and hydrogen. So the product of gasification, as you could probably guess, is a gas. It's actually a mixture of gases that we call syngas. It's a mixture of carbon monoxide and hydrogen. And those two can be used in Fischer-Tropsch synthesis, which is a series of chemical reactions to produce things like alkanes or other products. Or they can be combusted directly to generate heat, and the heat can be used to boil water, generate steam, which turns a turbine to generate electricity. In contrast, pyrolysis is a little different. This pyrolysis is actually the thermochemical decomposition of biomass or any other thing in the absence of oxygen, somewhere between 400 and 600 degrees C. So that's very important that it occurs in the absence of oxygen, which means that it is not combustion. We're not actually burning the biomass as you would in a fire. It's a different process. So the products of pyrolysis include a liquid, which we call bio-oil, a solid, which we call biochar, and other non-condensable gases. And we'll go over all of those things in a moment. And it turns out that the liquid product is especially important to research and development because it can ostensibly be used as a direct replacement for petroleum and all of the fuels and chemicals and other products that we derive from it. And I say ostensibly, we'll go over some properties of bio-oil that make it a little challenging to directly incorporate into petroleum infrastructure. So before we jump into pyrolysis, I'll mention that we're not going to really talk about gasification today in the interest of time. We're going to go over more about pyrolysis and the generation of biochar and bio-oil. And that's the research that I'm currently involved with at the CRC is on pyrolysis. So we'll focus on pyrolysis for today, but before we talk more about pyrolysis, we'll talk a little bit more about the chemical composition of biomass, and it might be a little difficult to see, but we're talking about, of course, lignocellulosic biomass, which, as many of you are probably aware, is sort of a fancy way of saying non-edible or non-food biomass. It's an important distinction because we're talking about something that can't be used as food. It's biomass material like grasses or trees, hardwoods and softwoods, or forest or agricultural residues that Tim talked about that we're using in these processes, and not actually food. So, of course, as the name implies, lignocellulosic biomass is comprised primarily of cellulose, hemicellulose, and lignin, and you can sort of see the chemical composition of those there, and we'll talk more about those later too. And you can kind of see the cartoon there of where those things are located in the cell wall. But if you look at the pie chart, these are all going to be ranges that Tim was showing you. The cellulose and lignin content of even within the same species of biomass can vary. But primarily we're looking at about 40% cellulose, 20% hemicellulose, and 25% lignin. Then there's those inorganic components that we call ash, and those are the inorganic species that plants need to grow and develop. I actually just overseeded my lawn for the fall and put fertilizer down, so that's what we're talking about, those inorganic components. There's also extractives, things like perfumes, flavoring agents, those types of things that come from biomass, and then other components as well. So we're going to talk about fast pyrolysis of biomass to produce a liquid product. And I have sort of a cartoon schematic here that we'll go through kind of quickly now, but we'll focus on each one of these steps in a little more detail as we go. And the point here is that we want to generate this liquid product called bio-oil because it's very similar to crude oil, and in the United States especially, we have infrastructure to deal with liquid products like crude oil or bio-oil. And so if we can turn biomass, which is a solid product, into a liquid product, then we already have the infrastructure in place to deal with that. And hopefully it's just a matter of substituting biomass for crude oil to generate the same products. Okay, so the idea, if we start at number one, the idea is to feed the biomass via an auger system into a pyrolysis reactor. That's number two there. And remember, it's important to recall that pyrolysis occurs in the absence of oxygen. So it's actually a relatively complex system that allows us to feed the biomass in the absence of oxygen into the pyrolyzer. The pyrolyzer is heated to the desired temperature, somewhere between 400 and 600 degrees. We'll go over the different types of pyrolysis reactors too. And the biomass pyrolyzes, and the gases and any entrained solids travel out of the top of the reactor towards number three into a cyclone, that's number four. And the cyclone functions to separate any entrained solids in that gas from the gaseous product that we're interested in. And the solids fall out of the reactor towards the bottom as biochar, which we'll talk more about. And the gases are then passed on through number five to number six, the condenser. And the condenser cools the gases off from that very hot temperature where they were pyrolyzed so that they condense into the liquid product, the bio-oil. And then anything that doesn't condense in that condenser is passed on to what's called an electrostatic precipitator. That's number seven. And there again, there's some more condensation that occurs so that we derive more liquid product from the gaseous stream. And then at number eight, any of those things that do not precipitate or do not condense, or those non-condensable gases, we can actually recycle and reuse. They're passed all the way back around to number nine, the burner. Anything that's combustible is combusted, which can generate heat for our process. And anything that's not combustible will be passed back to the bottom of the reactor to fluidize the reactor itself. So I'm going to go over these individual steps in a little more detail. And I apologize here, it looks like the figures got kind of garbled. But if we talk about the front end, we're talking about an auger, and you can see that in the background. An auger is it's sort of a fancy name for a screw, right? The screw actually feeds the biomass particles directly into the pyrolyzer. So again, because we're pyrolyzing in the absence of oxygen, we can't just open the top of the reactor and shovel biomass in. It has to be fed in the presence of an inert gas, typically something like nitrogen, so that we eliminate all of the oxygen from the reaction, because if there's oxygen around, then we're actually just combusting the biomass. We're just burning it as opposed to pyrolyzing it. And it's fed into this reactor. There's different types of pyrolysis reactors, but the one that I'm attempting to show here anyway is called a fluidized bed reactor, and it's a pretty common reactor. And in a fluidized bed, there's actually a fluidizing material. It's typically something like sand, and that's what's heated to the high temperature of 400 or 600 degrees. And when the biomass touches that sand is when it pyrolyzes, and the gases pass out of the top of the reactor and are fed through the rest of the system, and along with any solid products. And you can see that there's some gas there at the bottom that's used to fluidize the bed. So what we have is it looks very much like a pot of boiling water, except what we have is really hot sand that's sort of bubbling. And because we use the solid sand as opposed to a liquid, we can heat it up to a much higher temperature to do these reactions. So as the gases, and like I said, any of those entrained solids, the solids that escape as well, pass into the cyclone, and we collect biochar, and that's the first product that we get from fast pyrolysis, that solid product, which we'll talk more about in a moment. But I wanted to talk about the cyclone too. If you have ever worked in or have a wood shop, you probably are familiar with a cyclone. It's how you get the sawdust out of the air, and it works very much the same way in the pyrolysis reactor, in that any of the gases that come out of the reactor are passed in the cyclone, and the cyclone has got this cyclonic shape because it forces the gases into a vortex, and the solid particles have sufficient inertia where they can't be forced into that vortex, so they hit the sides of the cyclone and fall out of the bottom as biochar, and that's what we collect as biochar. And the cleaned gases can then be passed through the top into the next step for pyrolysis for further reaction. So let's talk a little bit about biochar. Like I said, this is the solid product of fast pyrolysis, and it's comprised mostly of carbon and also contains the inorganic ash that was in the biomass to begin with. The ash components, things like magnesium and potassium and sodium, those things that you put on your grass or on your plants as fertilizer, don't go anywhere they don't change during fast pyrolysis. They're actually still in either the ash or the oil that we get at the end. And so here is one way to collect those via this biochar. So the char is just carbon. It's actually very porous and has found some use as a soil amendment. So you can actually put this in the ground, much like you would fertilizer, to amend the soil, make it better for plants that you're trying to grow. And it's great as a soil amendment because it readily absorbs water because it's so porous. And it also contains those inorganic nutrients that you would otherwise be putting on in the form of fertilizer. It's already in the biochar. And because it's porous, it can actually house some beneficial soil microorganisms that help maintain the quality of the soil. We also call biochar recalcitrant carbon, whereas when you combust biomass or anything that contains carbon and you form carbon dioxide, which is released into the atmosphere, biochar is carbon that's in a solid form that we actually bury in the ground, so it's not released into the atmosphere and doesn't contribute to anthropogenic climate change. Okay, so if we go back, after we've collected the biochar, now we just have the gaseous products of pyrolysis between 4 and 5, and those are passed to the first condenser there. And a condenser is pretty much exactly what it sounds like, just probably a metal tube that has say cold water running around the outside of it to cool the walls of the tube, and the pyrolysis vapors will condense on the surface of that tube, much like water condenses on the surface of your drink when you're outside in the summertime, and that condensate then falls out at the bottom, and we collect that as bio-oil. And I have a picture here of some bio-oil, and you'll notice it looks a lot like crude oil. You know, if you've seen the Beverly Hillbillies, they talk about black gold or Texas tea, right? So it definitely does look like crude oil, and that's probably where the similarities end. But we'll talk a little bit more about bio-oil in a moment. So the last the last step, which is sort of optional, in fact, the reactor, some reactors don't contain an electrostatic precipitator, but it's useful to remove even more of the gaseous materials from the stream to collect additional bio-oil products. And we'll talk a little bit about electrostatic precipitation. In this process, you just take your gas molecules and you pass them over an electrode. And as they pass over this electrode where there's this large potential that's produced, they get ionized. And when those ionized particles pass through the opposite electrode, those red plates, they become attracted to it. And when they hit the plate, there's a charge recombination that occurs, and those neutral particles then fall out of the gas stream and are collected, and that's how we collect additional bio-oil. And so I had down there at the bottom of the slide, in quotes, fly ash. You may have heard of fly ash. In fact, people from the area here in East Tennessee might remember the fly ash spill at the coal plant in Kingston, Tennessee in 2008. Fly ash is actually removed from when you combust coal using electrostatic precipitation. It's a pretty common process in these industrial processes to remove particles from gases so that you can release clean gas into the environment. So the last bit is the non-condensable gases. So now the only thing that's left in that gas stream from when we started with whole biomass way back at number 2 are the things that we can never condense, that do not condense at atmospheric pressure. So those are permanent gases like hydrogen or methane, carbon dioxide, carbon monoxide. Those gases are actually, we can reuse those. We can send them right back to our burner at number 9 in the bottom left. And anything that will combust, we burn to generate heat for our pyrolyzer, for our reaction, so that we can get up to that 400 to 600 degrees C. And there's one last little bit that didn't make it on there, but the last part then are the gases that do not combust. Those are the things that are left over, like carbon dioxide or maybe nitrogen, that will pass directly into the pyrolyzer to actually fluidize that material. So that gas that comes into the bottom and makes the fluidizing material bubble, we can use that too. So we can use every part of the biomass that we put in directly in the process. So let's talk about some physical properties of bio-oil. I have a table here where I'm going to compare the properties of pyrolysis bio-oil and heavy fuel oil. So heavy fuel oil is what's left over when you take crude oil and distill away the gasoline, the diesel fuel, and the jet fuel. You're left with heavy fuel oil. And so there are properties here on this table like moisture content. It's less than it's about 1/10 water. It's mostly hydrocarbons. Specific gravity is a property where you compare the density of the material you're looking at to the density of a known material. So in this case, it's water. Specific gravity of 0.94 means it's less dense than water. And then the elemental composition, it's about 85% carbon, which is useful for us because we can turn that into products and fuels. About 11% hydrogen and very little oxygen, nitrogen, or ash content. HHV is high heating value, so that's the amount of energy that you get out when you burn. In this case, a kilogram of material, you get 40 megajoules of energy. It's going to be useful for comparative purposes in a moment. Viscosity, 180 centipoise, means it's pretty viscous. It's really thick. It has a very high resistance to flow. It's about 1 weight% solids, and if you take this material and you put it in a fractional distillation column, like you would in a petrochemical refinery, you can use about 99% of it. In fact, we'll use all of it. There's 1% that's left over as residue in the bottom that we use for things like asphalt. But 99% of it distills over, and we can use it for other products. Unfortunately, the properties for the bio-oil don't look like they're going to come up, but I can go over with you that it turns out in the column for bio-oil, the moisture content it can be as high as 50%. That's pretty high. We hope to get around 30%, but a lot of bio-oil is actually just water. As a result, it has a pH. The pH is very low. It's highly acidic, which is not good for the engineered components that I've been showing you. All those tubes are made of stainless steel, and they react unfavorably with acidic liquids. It has a high specific gravity. It's actually more dense than water. And the elemental composition is not at all the same as heavy fuel oil. It's about 50% carbon and can be upwards of 40% oxygen. And so the problem, all of the things that I've told you about so far, moisture content, acidity, its low heating value, come from the fact that it has a very high oxygen content. And it turns out that the distillation residue at the very bottom is about 50 weight %, which means that if we try to distill heavy fuel oil, 99% of it more or less distills over. About 50% of bio oil will distill. The rest of it is left in the distillation pot. It's recalcitrant material that we really have difficulty distilling and using in other processes. So how do we overcome the properties of bio oil that we don't like? Well, the research in my lab and in other labs at the CRC and in the Ibis Partnership deals with catalysis and using catalysts to change the properties of the bio oil or the pyrolysis oil vapors into something that's more favorable or something that we want. So in general, catalysts are molecular species that alter reaction rates. They speed up reactions. You can have a homogeneous or a heterogeneous catalyst. Homogeneous catalysts occur in the same phase as the reactants that you're talking about, and heterogeneous catalysts occur in a different phase. So what I mean is, if you think about pyrolysis, you have these vaporous, this gaseous material. And if you have a solid catalyst, then the solid is a different physical phase than the gas. So we have a heterogeneous catalyst system. And that's primarily what we use when we do catalytic fast pyrolysis, our heterogeneous catalyst systems. Excuse me, I should tell you that over 90% of all industrially produced chemicals in the world today involve at least one catalytic step. So just about everything that you purchase that is made from chemicals is probably had a catalyst involved somewhere in its production. And I should also tell you that in 2013, demand for just catalysts was $16.3 billion, which equates to about 1/10 of 1% of the gross domestic product of the United States. Meaning that doesn't even take into account the cost of the products that you made. Just to buy the catalyst to do the process required $16.3 billion in 2013. That's worldwide. I should also put a plug in that between the years of 2001 and 2010, 6 of the 10 Nobel Prizes in chemistry were awarded for research conducted on catalysts and other catalytic mechanisms. So it just goes to show that there's tremendous scientific, industrial, and economic drivers for catalysis and catalytic research. In the bottom right corner there, it's just sort of a schematic representation of how a catalyst works. If we can lower that energy barrier, then we can speed up the reaction rate. That reaction progress happens much more quickly. So whereas we've been talking about fast pyrolysis, you can actually do what's called catalytic fast pyrolysis, where you add a catalyst species to alter the composition of the vapors and or the oil that you get at the very end. And you can add catalyst species, if you look at the cartoon again, essentially anywhere in the process, but a lot of research is conducted that deals with catalysts either in position A or B or C or somewhere around B or C. And we'll talk about what those are and what those mean. So if you put your catalyst directly in the pyrolysis reactor, you are conducting what's called in situ catalytic fast pyrolysis. And in situ just means on site. It's exactly where the pyrolysis is occurring. So the catalyst species itself is in direct contact with the biomass. And so you essentially eliminate many issues with mass and heat transfer because your catalyst is actually touching the material that it's trying to convert into something more useful. In addition, you can affect the regeneration of your catalyst if you need to regenerate it directly on stream. If you remember the diagram of the fluidized bed reactor, you can actually take the solid material out of the reactor and replace it with fresh catalyst material if that's what you want it to do. Unfortunately, the catalyst being in direct contact with the biomass is also bad for the catalyst. It's good for the conversion, but it's bad for the biomass, or bad for the catalyst rather, because coking and fouling can occur. So coking is when the carbon in the biomass is deposited directly on the surface of the catalyst, and it actually physically blocks additional reactions from taking place on the catalyst surface. And fouling occurs when those inorganic materials that are present in the biomass actually chemically react. They could also physically react with the catalyst itself, and they can alter the chemical composition of the catalyst directly. In addition, if you put your catalyst directly in the fluidized bed, you can physically stress your catalyst and the support because they're sort of smashing around in there with the fluidizing material and also with the biomass at really high temperature. You start to pulverize the catalyst and change its morphology, at least on the macroscopic level. So because of that, we can also put catalysts outside of the pyrolysis reactor rather, in positions like B or C. And if we do that, then that's called ex situ catalytic fast pyrolysis, where we put the catalyst away from the biomass. We're actually catalyzing reactions in the vapor phase of pyrolysis. And this is good because the catalyst is then physically separated. So there's less likely that things like coking and fouling could be an issue, although we find, depending on the catalyst composition, those still can be problematic. But actually physically separating it from the biomass can be very helpful to mitigate those effects. It's also less susceptible to fouling and physical destruction. You know, if we put the catalyst after, say, the cyclone, then hopefully we've removed many of those entrained inorganic species. They're stuck on the biochar, and they're not actually making it to the catalyst species, and they're not fouling the catalyst. And the catalyst is in what's called a fixed bed, so it's sitting at elevated temperature, but it's not being smashed around by biomass or other fluidizing material. So it's less likely that it will become physically stressed during the reaction. However, you could think about the reaction taking place at a lower temperature. As we get further away from the pyrolytic reactor, the temperature gets lower and lower until we get to the condenser. And this means that the kinetics could be slower, the reaction rate could take more time. You know, you think about when you cook spaghetti, the reason you boil the water is because the spaghetti cooks faster at the higher temperature. Same thing here, the reaction will take place faster at the higher temperature inside the inside the pyrolysis reactor. So we have to artificially raise the temperature further downstream to get those faster kinetics. It's also sometimes difficult to regenerate catalysts on stream if they're in this ex situ environment. Typically you have to bypass the catalyst and send it through fresh catalyst, or you have to actually stop your reaction and replace the catalyst. And of course time is money, so anytime you stop the reaction you're losing money or you're losing products coming out. Okay, so what exactly do we want to do with our catalysts? Well, one aspect would be catalytic deoxygenation. If you think back to that table that I showed you, biomass or bio oil has a very high oxygen content. And if you remember that biomass is composed primarily of cellulose, hemicellulose, and lignin, and the chemical compositions are kind of shown here in these cartoons, then it should be pretty obvious that because cellulose, hemicellulose, and lignin themselves contain lots of oxygen, that the products of fast pyrolysis would then also contain lots of oxygen. And we are pretty certain that the reason that bio-oil has such deleterious properties like low pH, low viscosity, low heating value is because of the high oxygen content. So the question becomes, can we catalytically remove oxygen atoms selectively to produce things like furans in the box could be produced from cellulose and hemicellulose, or in particular from lignin we might be able to selectively produce BTX, which is a mixture of benzene, toluene, and xylene that I'll just talk very briefly about. I'll show you the BTX chain here. You can see that already industrially we use benzene, toluene, and xylene to produce a host of things, including polyester, polyurethane, nylon, other synthetic fabrics, phenolic resins, food packaging, plasticizers, paints, solvents, etc. In fact, BTX is one of the top 5 chemicals produced in the world today. And the idea is to potentially produce this from renewable sources so that we do not have to produce it from petroleum. So I'm just going to wrap up really quickly, and I'll let you read over those conclusions, and if we have any time, I can answer some questions. Otherwise, Thanks very much for your attention.
Thanks, Steve. Okay, next up we have Maggie Davis. Maggie comes from Oak Ridge National Laboratory's Environmental Sciences Division and is an economic geographer who works on international bioenergy issues, feedstock supply, and agricultural policy modeling, including the upcoming million-ton 2016. Maggie holds a Master's in Forestry from the University of Tennessee, through which she worked with small-scale eucalyptus farmers in Brazil. We're excited to have Maggie. I'm glad she came over from Oak Ridge, and I'll let her take over.
All right, thank you. And first off, I have to apologize for my voice. It's the time for colds, and I seem to have picked one up yesterday. So to start off with, I do want to thank the folks that I collaborate with, which are both at Oak Ridge National Laboratory, Keith Klein, and then also externally, Diego Goldine and Fred Gatala. Fred is located in Canada and Diego is located in Argentina. And the two of them served as the conveners of Working Group 4 on ISO 13065, which is the focus of the talk. I also want to thank our sponsors at the Bioenergy Technologies Office. So an outline. I'll give a little bit of a background on indirect effects. I am switching gears from the previous talk to a more broad global focus and the trade of bioenergy. So then I will talk about the relevance, of course, to the U.S. and the U.S. industry, and the approach that we took to looking at indirect effects under ISO 13065 and Working Group 4. Then we will also talk about the conclusions that we drew under Working Group 4. So for the background, I want to focus on, or I want to first clarify what indirect effects are by actually talking about what they are not. So they are not measurable, they're not under the direct control of the economic operator, and they're not caused by the process being analyzed. Those three criteria actually define direct effects. So indirect effects, as described by Finkenbeiner in 2013, are, the indirect land use change. He said that they cannot be measured or observed. And the RSB, Roundtable on Sustainable Biomaterials, has said that these are macro-level impacts and are likely to be beyond the control of the individual farmer or biofuels producer. So herein lies the problem with indirect effects. They're unable to be measured, and they're hard to attribute to a process or a producer. And yet there is general agreement, or there's a movement within the general population, policymakers, many researchers, environmentalists as well, that indirect effects are important and that they need to be addressed, even though they can't be measured and cannot be attributed to a process. So more on relevance, the EU's Renewable Energy Directive and the US's Energy Independence and Security Act, under which the RFS2 was implemented. These are two policy decisions that actually take into account indirect effects. Generally, these policies were implemented to lower emissions in the transport sector, diversify the fuel supply, increase fuel security, provide new markets for agricultural products, foster value-adding innovation, and also reduce greenhouse gas emissions. And in general, they were supposed to have other environmental or social merit. So right about the time that these policies were being passed, the concepts of sustainability and life cycle assessment had entered the vernacular of policymaking as well. So getting back to why this matters, why are we talking about EU policy? Well, you can see from this map and the next one that ethanol trade and bioenergy trade in general is a big deal for the U.S. We are exporting more in 2011 than we did in 2009, and even more in 2014. So we are actually exporting about 6% of our domestic production of ethanol, which far surpasses the nearest competitor, which is Brazil. In 2014 alone, that was worth $1.3 billion just in ethanol. So that's not taking into account biodiesel or other bioproducts, bioenergy sources such as wood pellets, which is also a big deal for the U.S. So you can also see from this graph that we are primarily exporting to the EU, Canada, and Brazil, as well as other countries, but there has been a shift in recent years to other countries, and so I did include, just for information, an update on that. The UAE is actually drawing a lot of their energy needs from bioenergy when it's cheap, when it's cheaper than petroleum. And so that's a big market for the U.S. right now, as well as the Philippines and India. So getting back to the topic at hand, you see that international trade of bioenergy is a big industry and is growing in importance as we grow our bioeconomy. But what about indirect effects? Indirect effects can actually be a major barrier to acceptance of bioenergy nationally and globally. So the brief background on indirect effects is that Searchinger was among the first to get wide publicity. He had an article published in Science in 2009, and he had very, very high estimates of greenhouse gas emissions coming from indirect land use change. This received a lot of attention, and policymakers began to respond. There were even some high-level articles, such as Mazed and Confused, in The Economist that got a lot of publicity. And this was although researchers and scientists argued for additional scrutiny, and there were many rebuttals by scientists engaged in life cycle analyses that advised a caution. There's one article by Wang and Hawk in my references if anyone's interested. So even though this had gained traction and scientists were arguing for people to put the brakes on jumping to too many conclusions, it was included in the policy making federally and in California. And embedded in these policies was the obligation that required fuels should be evaluated for their sustainability and assessed for their emissions on a full life cycle basis, or throughout the entire life of the product from what they call cradle to grave, which grave is often the use or the disposal of the fuel source. So in practice, this meant that the LCAs of the fuels should include indirect effects, and that their sustainability analyses would be performed by either the responsible government agency or via sustainability certification schemes. So from 2007 onward, there was a flurry of activity by multiple groups to create certification programs that could address these life cycle analyses and indirect effects that policy was requiring. So that brings us to my approach, or our approach, under ISO 13065 in looking at indirect effects. So a little background on ISO. I wasn't familiar with it before I joined the project committee, so figure I'd give the background for most people who aren't that familiar with it either. It does have a global reach. There are 163 member countries with almost 20,000 published international standards. Rio 1992, there was a series of environmental standards that came out of that, the 14,000 series, and they have actually received a lot of really good feedback on those. They're applied in 155 countries, and there are over 250,000 users. So coming out of that, ISO tackled social responsibility, which was a little more controversial. Their 26,000 series was published in 2010 and has been in use, although not as widespread use as their 14,000 series. So I'll skip the rest of this in interest of time. And I'll jump to who we are. So ISO created 13065. It's led by Brazil and Germany. And it is a standard that's looking at sustainability criteria of bioenergy. This is what we look like at the very last plenary meeting. A bunch of suits. Not everyone's in a suit, but you can tell there's a bunch of diversity as well. We have, let's see, I think there are over 30 countries represented in PC Project Committee 248 that developed this standard. The standard has been published as of just a month ago and is available on the ISO website. So I introduced the PC 248 mandate, so I'll skip that. But I do want to bring you guys to the working group 4 that was volunteer-based, pulling their members from the project committee, whoever had an interest and wanted to participate. And we had the mandate to report on the state of the science of indirect effects. I served as a secretariat to this working group with the 2 conveners out of Canada and Argentina, Fred Gatala and Diego Goldbein. There is general agreement in the scientific community that uncertainty in ILUC calculations is far beyond the acceptable for quantitative sciences. Finkenbeiner said that, and there are many other articles that have said that. And the contributing experts in Working Group 4, in general, they also agreed that ILUC models were yielding a broad range of calculations. Unfortunately, that's where the agreement stopped. There was a large amount of disagreement in the working group about which range was correct, the high end or the low end. And there seemed to be polarized opinions on whether or not these models were producing results that could accurately reflect the indirect effects of bioenergy production. So what we did is, over the course of 3 years, we reviewed over 160 journal articles published between 2008 and 2013, and we were able to come up with some conclusions based on consensus. So that meant that everyone in the working group agreed to these statements. It took us a long time to come up with just a short paragraph, and we have a lot of background information on why we were able to come to those conclusions on indirect effects. If anyone's interested, I can provide more details, including an upcoming paper on the process. So our results were that the state of the science in terms of evidence-based research is inconclusive or contradictory regarding indirect effects. We also highlighted that an economic operator should not be held responsible for indirect effects and variables that are outside the operator's control. This was a key statement that we presented to the project committee who was drafting the standard ISO 13065, That was just a recommendation, and it was taken into account whenever they were actually drafting indicators and methodology for dealing with effects of bioenergy. We also highlighted that recent modeling of indirect effects has highlighted potential impacts as well as the high variability in results, though much of the modeling thus far has relied on assumptions that may not be supported by empirical evidence. So to date, there has been limited causal analysis to support assumptions in underlying indirect effects modeling. That was another conclusion of the working group, and that there needs to be equitable treatment of direct and indirect effects for any energy options being analyzed, including baseline fuels that would be replaced by bioenergy sources. So that would be putting bioenergy even keel with other energy sources because the world uses energy. If it's not bioenergy, it's going to be something. And ultimately, the project committee decided not to include direct effects in the standard. The final wording, again, this standard is available on the ISO project, or I'm sorry, the ISO main website, and I have a link to that website in my references at the end. It's available for purchase. Unfortunately, I can't share it, but I am able to share this conclusion on direct and indirect effects, which is that in developing this international standard, we considered these issues very carefully, and in the end, they decided that this international standard considers the measurable environmental, social, and economic effects that are under the direct control of the economic operator and caused by the process being assessed. We also had a big win within the standard by focusing the entire standard on a science-based approach whenever possible. And the standard does define what that is, and it gives a preference to science that's based on empirical evidence. So bringing it back to why this matters, it's the global trade of bioenergy has been increasing over the last several years and is projected to continue to increase. This is a 2010 map of global wood pellet trade, but it's even increased from that in recent years. And there is actually a movement within the EU. You can see a lot of the pellets coming out of the US and Canada are going into the EU, but there is a question of what the indirect effects of these cultivation of these feedstocks are, and it really could have major implications for the exports of wood pellets and bioenergy in general. So we provide a path forward or recommendations, and that is that a science-based approach be the preference for when dealing with indirect effects, and that you should focus more on a causal analysis rather than